Let's talk about the conservation of energy. We've talked about an object in motion, and we said it has kinetic energy equal to 1/2 mv squared as derived in the previous video. Kinetic energy is the energy of motion. Then we saw an object raised up from the floor, and we said it had potential energy, and the formula given is mgh, also derived in the previous video. You can think of potential energy as the energy of position. Because the block is up here, it has the potential to come back down, doing that amount of work. When we say we have conservation of energy, the total kinetic and potential energies of a system remains constant. Let's look at this example to see what we mean. We're going to drop a block to the floor. What is the final velocity upon impact? You have to ask yourself, what kind of energy do we have initially? What kind of energy do we have at the end? And then we're going to say that they're the same. You'll say energy initial equals the energy final. We can have a kinetic energy and a potential energy initially. And we can have a kinetic energy and a potential energy final. Ask yourself, what is the formula for kinetic energy? 1/2 mv initial squared. What's the formula for potential energy? We have mgh, initial. Filling in the rest of the formulas, we can now ask ourselves, what goes here? The initial velocity is 0, so there's no initial kinetic energy. The height final is 0, so there's no final potential energy. So this is what we're left with. We can plug in our data, and we have 196 joules of potential energy. As the object falls, this potential energy is converted to kinetic energy, and that's why we're setting it equal to 1/2 mv squared. Do the math, and you get 8.85 meters per second. Now, I'm sure you saw that you don't really need to calculate the energies. The mass cancels, and we get a formula for the final velocity. Does it look familiar? Yeah, it's the forgotten formula from kinematics. The delta D is just the h, and the VI is not here because we had an initial velocity of 0. If this is our system and there's no other forces involved, then we can say the energy is conserved. We don't have me pushing on this, adding energy to it, and we don't have friction dragging out any waste heat. So the mechanical energy is conserved. Let's try another example. We have a cart moving at 3 meters per second, frictionless. It encounters a hill. How high up will it go? We need to identify all the variables at the initial position and then the variables at the final position. There's no friction involved. I'm not pushing on the cart. So for this system, we can say the energy is conserved. Again, we just set up KE initial plus PE initial equals KE final plus PE final. What is the kinetic energy initial? Do the math, I get 45 joules. We're at the bottom of the hill, we have 0 PE. Now, when we say how high up will it go, we have to realize that the velocity up here is going to be 0. So we're going to have 0 joules of kinetic energy at the end. Well, we're going to have 45 joules of potential energy at the end. The kinetic energy turned into potential energy. mgh, and we get 0.459 meters. Of course, we don't have to calculate the energy. We can cancel the masses and derive an equation for the height final. So what would be the height final if we made the ramp tilt higher? When you look at the equations, the angle never came into play. The height is all that matters. The angle will change the length of the incline, but the final height will be the same. Let's take a look at this roller coaster. The cart is 100 kilograms, traveling at 20 meters per second, starting with an initial height of 3 meters. The ground is going to be height 0. It's going to roll and coast up this hill 15 meters above the ground. What's the final velocity? Well, assuming this track is frictionless, we can say the energy initial equals the energy final. You should always start your problems off by writing this. Now let's fill in the energies where we can. Looks like we've got kinetic energy. 1/2 mv squared gives us 20,000 joules. mgh initial gives us 2,940 joules. We don't know the velocity, so we can't calculate the kinetic energy final just yet, but we can calculate the potential energy final from mgh. We get 14,700 joules, and that is exactly how much we'll have at the end. So we'll now be able to solve for the kinetic energy final. It gives us 8,240 joules. And again, using 1/2 mv final squared, we get 12.84 meters per second. Now just think about this. If you made a mistake, you might be able to pick it up because that velocity has to be smaller than that one. Let's just take a look at all the variables now. Watch what happens if we bring mgh initial over to this side. We have mgh final minus mgh initial. We can factor out the mg. We have mgh final minus h initial. What does this mean on the diagram? We're taking the final height, subtracting the initial height. It gives us the change in height. If both the beginning and the final height were higher, or the beginning and the final height were lower, it's the difference that matters. So we can just as easily make this the initial height 0. And just say the roller coaster went from a height of 0 to a height of 12 meters. And that's what would go in here. So it could save us a step just by drawing the diagram a little bit differently. We'll emphasize the idea with a demonstration on just lifting an object up and then lowering it down. At this height, we can say the potential energy is 0 joules. Now let's say I raise this block up 2 meters. Maybe I have 10 joules now. The initial and final gives me a change of positive 10 joules. Well, what if this was the initial position and that was the final position? When it comes down, I can say that we lost 10 joules. And what if I keep on lowering it? If I go down another 2 meters, I'm going to lose another 10 joules, and I will now be at negative 10 joules. Is it really possible to have negative potential energy? All that means is we would have to add 10 joules to get back up to 0. Well, we could have just as easily called this level 0 joules. Bringing the block up to here, I'd now have 10 joules. It's 10 joules more than that level. And bringing the block all the way up to the top, I'd have to go up another 10 joules. So I'm going to go from 10 to 20 joules. So as you can see, it's really arbitrary. It's up to us to decide where we want to call the 0 energy level. In all of our energy problems, it's going to be the change in energy that matters. Okay, so let's say I have a pendulum that's 1.5 meters long, and we have a mass of 300 grams. I release it from rest, and it starts to swing down. Let's take a look at the energies to find the final velocity. It would make sense to call the lowest position 0 height. That makes the initial height 1.5 meters and the final height 0 meters. So what kind of energy do we have in the beginning? Of course, we only have potential energy, and we don't have any kinetic energy because the velocity is 0. At the end, we don't have any potential energy because the height is 0. So we'll say the initial potential energy is all converted into a final kinetic energy. Now, I see kids all the time start out with a problem like this, and they say, there's a law of physics that says the initial potential energy is equal to the final kinetic energy. And that's not true. It all depends on what system you're looking at, what the problem is. Never start off like this because it's just plain wrong. So please always start with energy initial equals energy final, and then you can eliminate these terms and end up with this. And we get 5.42 meters per second. Now we should note that if we drop a ball from the same height, by the time it gets down to here, it'll have the same final velocity. It's the same formula. It's just that the rope is redirecting it and making it go in a different direction. You see, you have to take a look at the force of the rope. It's always perpendicular to the velocity. And since work is force parallel times distance, the tension in the rope can do no work. It doesn't change the magnitude of this velocity, it just changes the direction. Well, what would happen if we wanted to know the final velocity when this thing has fallen 40 degrees? Well, now you're going to have a potential energy final, which means you need a height final. How do you get that? Just like in the first week of school when we were doing the flagpole problem, you have to draw a horizontal line and make a right triangle out of this. You can take L sine theta and get 0.964 meters. Since this is also 1.5 meters, we can subtract 0.964 meters and get 0.536 meters for the height final. So here we have the height final. Here we have our height initial. We bring this term over to here. Hey, we get the 0.964 back. Well, that makes sense because it's this change in height that represents the loss of potential energy, and that's what we're calculating here. So just to eliminate a little math, you can make that height 0 and then just put in L sine theta for the initial height. And then we find the final velocity at that position. And we get 4.35 meters per second. Kind of makes sense. It's a smaller number than what we have here for the final at the bottom. Well, you might be wondering, hey, it's a pendulum. Why not use our simple harmonic motion formulas to find the final velocity? Not going to work here because we're way back past the 30-degree pullback. We've pulled it back to 90 degrees. Now let's go back to our original setup and ask ourselves, what would a sketch of the potential energy versus the angle fallen would look like? For this setup, at 0 degrees, we're at the release point. We have a lot of potential energy. It's all potential. At the bottom, we've come down 90 degrees. And now we're at the bottom. We have no potential energy. And of course, the question is this a straight line? Could it be a curve? Could it curve that way? Maybe this way. Let's take a look at how much we dropped in the beginning. In the beginning, we drop a lot for an angle. We lose a lot of potential energy. As we swing down, this starts to level off and we don't drop as much. So we don't lose as much potential energy. And towards the end, we don't lose much at all. So the graph follows this curve. It's part of a sine curve. Now, what about that kinetic energy? Where does it come from? As we lose potential energy, we're gaining kinetic. So now, will this go up as a straight line? Will it curve up this way? Will it curve up that way? Well, let's think about how much potential energy we lose. We lose a lot in the beginning. Whatever PE we lose, we have to gain KE. In the next interval, we don't lose that much PE. Well, we just have to gain the same amount, but it's not as much as before. And at the end, we have to have the same KE as the PE was in the beginning. There's nothing else going on here. So what do you think the total energy will look like? Well, the total energy is the energy of PE and KE combined. At any point in the graph, you come up to KE, add that to whatever you have for your PE, and you'll be at this level. Well, that's true at the beginning, and that's true at the end. That's as much KE as you have because you have no PE. Everywhere along here, it's going to be the same value. This means the total energy stays constant. It's another way of saying conservation of energy. Whatever energy we lose in PE, we gain in KE, keeping that constant. Let's release a block from rest on an incline. It's going to come down 3 meters. The incline is 25 degrees. We reach a final velocity of 5 meters per second. Is energy conserved? Well, pause the video and try to figure that out first. You have to ask yourself, what kind of energy do we have initially? What kind do we have at the end? Again, we have a velocity of 0, so this goes away. And we're down at the ground, so that goes away. Using MGH, we have 294 joules. And using 1/2 mv squared, we get 125 joules of kinetic energy. What happened? Take a guess. Must have been some friction. And which way did that friction act? Must have been going uphill. That friction times this distance, we could say, is an input of negative work. When we bring that negative work done by friction to this side, it becomes a positive value, and we call it waste heat. We say the 125 joules stays in the system, but the waste heat leaves and goes out into the environment. It's waste heat because it's no longer contained inside here. Unlike the potential energy, this cannot do any work. So how much waste heat do we have? 169 joules. And if we're talking the work done by friction, we have to say it's negative 169 joules. So what causes all this work done by friction? It's got to be a force of friction times the distance. Well, they have to be parallel to each other. We can see the force of friction is parallel to the plane. So the length of the incline must be the associated distance. A little trigonometry gets us 7.1 meters for that distance. Plugging in the distance, we can calculate the force. And we get a force of friction of 23.8 newtons with a negative sign indicating it's going up the plane while the block is going down the plane. Well, if you wanted to, you could calculate the mu k from the force of friction and the normal force. One more example. How about we're going to drag this block up the hill? I'm going to use 30 newtons. I'll pull parallel to the plane, 6 meters. What's the final velocity going to be? Now again, you might want to pause this video and try it first. Well, let's see if energy initial equals the energy final. And that term plus waste heat we had in the last example, that's not going to be there because there's no friction. Let's assume the initial height here is 0. So the PE initial goes away. Do we have a KE initial? Yeah, I see that the initial velocity is 2 meters per second. Well, that's 10 joules of initial kinetic energy. What's the final potential energy? Well, you do the trig and you get a final height of 2.05 meters. And we get 100.5 joules up to the top for the potential energy. But wait a minute, how does that happen? How do we go from 10 joules to 100.5 joules and still have something left over for a final velocity? Well, maybe it has something to do with the work that I did. My work is the force parallel times the distance. And that work is going into these energies. So we'll add it right here. It's a positive work. So I'm adding 180 joules of work to the 10 joules that I have initially of kinetic energy. And that'll leave me with 89.5 joules of kinetic energy. And of course, now we can use 1/2 mv squared, and we get 5.98 meters per second. So in these examples we've seen, so far we'd say that the energy initial equals the energy final. If there's no friction, this is what we have. If we do have friction, we're going to lose some of this energy to waste heat. And if we have positive work being done to the system, we add it here at the beginning. So this is our full statement regarding energy. You can find lots more examples to work on in the chapter notes and in the worksheets.